Hello guys, today we'll be on the 2019 Junior Balkan Math Olympiad Problem 1. So, find all prime numbers p for which there are non-negative integers x, y, and z such that the number a is equal to x to the p plus y to the p plus z to the p minus x minus y minus z is a product of exactly 3 distinct prime numbers. So, we want to, the step for this problem is to try to find what the 3 prime numbers can be. So, first thing we notice is that this expression is actually symmetric in x, y, and z. So, we can just permute any values we find among x, y, and z, and so we only have to handle x necessarily, because if x is, for example, 0 mod 5, then all the other ones can be 0 mod 5. And so on first look, this kind of reminds us of Fermat's little theorem, and so x to the p is equal to x mod p for any x, and this is Fermat's little theorem. So this means that this is equal to 0 mod p. So p is our first prime, which is pretty interesting. Okay, so p is our first prime. Now we want to see if we can find out any small primes. So let's let p be greater than 2. And so if p is greater than 2, then that means that first of all, we notice that if x is odd, then an odd power is an odd, and odd minus odd is even. And if x is even, then even to the any power is even, and even minus even is also even. So no matter what, this expression is always even, and this is always even, and this is always even. So which means that this entire expression is always even. And so that means that 2 is also a satisfying value, but this assumes that p is greater than 2. And so now let's assume p is greater than 3. If p is greater than 3, then let's test out if 3 works. We know that x squared is equal to 1 mod 3 by Euler's theorem, because any number to the power of totient is equal to 1 mod n. And this is another useful part in pre-Olympiad, I think, or Olympiad Geo, Olympiad number theory. So anyway, so since p is greater than 3, p is a odd prime that is greater than 2 and 3, so that means that any p, we can just subtract 2's over and over to get to 1. And so this means that x to the 1 is, and x minus x is 0, so all of them are 0 mod 3, so 3 is also a value. But this is assuming the values that p is greater than 2 is p and p is greater than 3. So now let's see if p equals 2 and p equals 3 works. So if p equals 2, then we have the values x squared minus x. What values can this expression take on? This can take on 0. This can take on 2 squared minus 2 is 2. 3 squared minus 3 is 6. 4 squared minus 4 is 12. 25 minus 5 is 20, and 36 minus 6 is 30. And so we know that 30 is the first one. That is the product of 3 distinct primes. There's 2 times 3 times 5. And so this is p in this case. But anyway, so 2 times 3 times 5, right? And so now this value can be achieved through 30, 0, and 0, obviously. So we can just set x as 6, y as 1, z as 1. And what does our expression yield? It yields 30. And so this means that p equals 2 does actually exist, does actually work. So this is off the table. So now we just have to test out p equals 3, and then we're all good to move on with the next step of the problem. So if p equals 3, then we have numbers in the form x cubed minus x. And so then the numbers are in the form 0, 8 minus 2 is 6, 27 minus 3 is 24. And what you have it, these also add up to 30, which is 2 times 3 times 5. And we can still use it because then p can be this value right here. P can be 3. So this means that we can have values x equals 1, y equals 2, and z equals 3 that all work. So p equals 3 is also satisfied. Now we know our 3 primes. Now we just want to see what numbers p work. And so let's delete this. So now let's test out p equals 5. We can still use that 30 is equal to 2 times 3 times 5. And we have to because we know that 2 and 3 are factors now. So then conveniently we know that 1 minus 1 is obviously 0, and then 32 minus 2 is 30. So we can have x equals 2, y equals 1, and z equals 1. So p equals 5 also works. So now what about p equals 7? If p equals 7, then this expression must be equal to the product of 2 times 3 times 7, or 42. But if we realize that the values that this expression can take on are 0, or 2 to the 7 minus 2 is 126. And 126 is always way bigger than 42. And so this expression, we notice that, for example, if x equals 1, then obviously it's 0. If x equals 2, then it's 2 to the p minus 2. So this expression is at least 2 to the p minus 2. This is the smallest value you can possibly take on. And so let's set this as greater than or equal to 2 to the p minus 2. So what we want to prove is that 2 to the p minus 2 is greater than 6p for all p is greater than 7. So we can do this with induction. The inductive step is p equals 7. Like I said, 126 is clearly greater than 42. Now, let's say there exists a number n that works. So this means that 2 to the n minus 2 is greater than 6n. So now we want to prove that 2 to the n plus 1 minus 2 is greater than 6 times n plus 1. And so how do we do this? So let me this writing was a little bit big. I'm just gonna put it up here. And same with this. So this is just induction. And so basically now what we can do is to get this, we multiply 2 on both sides. We get 2 to the n plus 1 minus 4 is greater than 12n. So that means that 2 to the n plus 1 minus 2 is greater than 12n 12n plus 2, right? And so now we know that 12n plus 2 is greater than 6n plus 6 because 6n is always greater than 4 for all p greater than 7. 12n plus 2 is always greater than 6n plus 6 so 12n plus 2 is always greater than 6n plus 6 for all p greater than 7. And so now we know that no values of p that are greater than 7 work. And so that means that the only values of p that can work are 2, 3, and 5. Thank you guys for watching. This is a very long video. I'll see you. Bye.